And we will turn it over to Kent Fisher to talk about lessons learned from Artemis 1 and some perspectives on the future. Kent.
Thanks, Kelsey. As she said, I'm going to talk about what our team, the Image Science Analysis Group, did for Artemis 1. I will preface initially that this is an engineering imagery group, so we focus on photogrammetry and other measurements for engineering purposes, not science. But I believe a lot of the lessons learned and things that we experienced during the first mission will be useful for the science team to understand and prepare for Artemis 2. Next slide, please. So a quick overview, Kelsey, I believe, showed the Artemis 2 overview. This is the Artemis 1 overview. It's a quite different mission. Artemis 2 is planned on about 10 days. Artemis 1 was about 25. And the main thing to note here is that we actually passed a lot closer on Artemis 1, about 81 to 82 miles off the surface than we will on Artemis 2, multiple orders of magnitude closer. And so it's one thing to clarify, and you'll see some images in this presentation that shows some beautiful shots close up on the moon. We will be a little bit further away, so those aren't exactly representative of what the scenes will be, but I do think we'll be able to get some good imagery during the mission. Next slide. Oh, sorry, Chelsea, you're going to have to click through. You can just click through 3 times. There you go. So here's an example of the types of image analysis that we did during the Artemis 1 mission, we'll do during Artemis 2. And these are different things measuring things like ICPS separation or FPC separation, parachute performance, things like the views for the service module and crew module inspections. And these are typical things that we do during imagery operations using various vehicle cameras and crew cameras when crew are flying, both on Orion, but also on other missions like commercial crew and ISS. And these types of measurements allow us to understand the performance of the vehicle, the state of the vehicle, and do operations appropriately. Next slide. To support this type of work, we have 2 rooms that we staff, one known as the Imagery Operations Center, staffed by the IoT or Imagery Operations team, and another known as ISAL or the Image Science and Analysis Lab. These two, you can go to the next slide. These 2 labs are next to each other, and you have basically the ops group, which you see in the top right there. And then kind of behind the wall is the imagery lab, and that is the group that's doing all of the image analysis. And so the Imagery Operations Center is probably most similar to how the Science Evaluation Room, which is the science back room that are supporting the Artemis missions, will work. These are folks that are on the voice loops talking to mission control, planning out operations and activities, working directly with vehicle data and downlinking stuff. While the Image Analysis Lab in the back is doing actual imagery assessments and photogrammetry analysis during the mission, during specific events. Next slide. Next slide. You can click through a couple times, Chelsea. So primary thing you'll hear here is the ADIM plan, train, fly, right? And so you want to plan and train how you're going to fly. And all these lessons learned are focused on the planning and training process because there is a lot of work that goes into doing these sort of operations. For example, the pre-flight planning for Artemis 1, our team supported over 90 FOD simulations. And on top of that, we held numerous what we call paper simulations with our counterparts in FOD and IRD, where we walk through different procedures, right? And so those 90 simulations are actual ones where we're on the loops, looking at data in the system and practicing processes. But there are some limitations to this, right? So during Artemis 1 planning, we didn't actually have high fidelity simulations that can fully realistically with actual cameras collect everything from the cameras through the camera controllers and down to the ground systems. And that was only capable when we had access to Lockheed's Martin's simulators. However, that was very limited. And so we don't know how much better access we'll have in Artemis 2. So you have to understand that during the mission was actually the first time that we had full end-to-end imagery operations, right? And so you have to be available to adapt on the fly and understand your systems really well so you can respond to differences in the operations than how you actually simulate. So next slide. Some examples of the types of pre-flight planning that we do, and these are examples of pre-visualizations as we call them. And so you see, for example, in the bottom left, on the left side is a model image, and then on the right is the actual image during the mission. Same with on the right, the bottom 2 images are from models, and then the top are actual images. And what we do is we go through and make these pre-visualizations so our partners, both in operations and engineering teams, the Orion teams, Lockheed Martin, understand the types of imagery that we can acquire, when we need to acquire it, what sort of camera settings we need. And these are all the sort of things that you'll have to do for science planning, understanding, at what moment will you be able to see what crater on the lunar surface and what camera settings do you need, You need to document all of this. It needs to be all laid out very well and planned so that when it happens during the mission, there's not going to be time to react. These events are very quick. For example, ISS observations, a target goes by in a handful of seconds, right? And so you've got not a lot of time to react, and so you need to have this all planned out beforehand and have all your camera settings, have all your understanding of the environmental conditions so you can adapt, planned out, modeled out, and then documented in procedures. Next slide. So an example of this is that the Artemis 1 test flight objectives were laid out in a long document name known as the Orion Multipurpose Crew Vehicle Program, EM1 and EM2 flight test objectives. There's a lot of these types of documents going, and this is something that both the PAO team will have to develop for their own plan, and the science team has started developing for this for Artemis 2. And this is where you document everything out, what types of views you want, when you want it, what camera settings you want, what you're going to do with the data afterwards. Are you going to try to downlink it? What's it going to be used for post-mission? These plans lay out there's a data analysis plan that lays out, okay, this imagery is being used for this engineering assessment. And a similar plan should probably be put together for understanding, okay, these images for the flyby are going to be used to meet X science objectives post-mission. So there's a lot of documentation, a lot of planning that has to go into this, both pre-planning for understanding simulation plans, planning for actual imagery operations during the mission, and then planning for how you're going to use the imagery that you collected afterwards, after the mission is concluded. Next slide. A prime example, and this isn't to call it PAO, but there wasn't a PAO imagery plan during or before Artemis 1. And then during the mission, there were a lot of requests for actual PAO imagery, which of course wasn't written down anywhere. There wasn't a documentation, and it caused a lot of on-the-fly work that had to be done to adapt and prepare and get these types of images. And so this is something that's being addressed in Artemis 2. There's a PAO imagery plan, and there's also going to be hopefully a science imagery plan that will lay out these things so it's all clear beforehand what is expected, what's required, and what's needed. But a couple considerations have to be understood. It's not as simple as saying have the crew take imagery of the lunar surface during the flyby. A lot of the requests that have come in for science imagery or science operations require vehicle maneuvers. And that means you have to talk with both the folks handling propulsion and fuel, folks handling the thermal systems, folks handling the communication systems. All of those will be impacted and all have to be assessed, modeled, and simulated to understand what can be met and what cannot be met. And so it's not just a matter of, okay, just the imagery team either, right? When we ask these have these sort of requests, like these PAO requests and the science requests, there's a lot of other teams that are impacted and have say. And for example, if the propulsion team comes and says, we don't have enough prop to do that maneuver, we can fight as much as we want to say we need the imagery or want the imagery, but ultimately the program has to make the decision, do we have enough fuel to make that maneuver needed to get that type of imagery requested? Some other random recommendations is, have people with the critical IT expertise needed to handle to work with this data. This stuff doesn't just all get dropped on a Google Drive during the mission, right? There's a lot of complex systems that have to be interacted with to access this imagery data, both during the mission and post-mission. So it's important to have the right people available to help navigate that. And then finally, one that's not very fun is export control. This does apply even internal to NASA. Distribution of imagery within NASA is restricted, and distribution external to NASA is restricted, and this must be planned out beforehand and get approval beforehand so that there's less delays in delivering imagery. Next slide. So just to summarize a handful of these recommendations, plan, and then train simulations. A lot of documentation, a lot of laying out procedures, a lot of meeting with different groups, and then practice it in simulations to understand all the data flows. Additionally, I know there's going to be a science evaluation room or science back room. I recommend having a certification process for the different roles that are going to be in there, whether it's someone running the science room, whether it's someone managing or interfacing with the imagery data, or other roles in there. We maintain a kind of certification process for our back rooms for our imagery operations center. And then of course, FOD has a whole certification process for all their flight controller seats. This is a good way to document and understand the training flow so that when you have people come and as it moves to future missions that may be more complex, like Artemis 3, you have something to build off of. Additionally, make sure you have the right personnel. It is a science room and you may want a bunch of scientists in there, but you also will have to have folks that are understanding how to work with the loop systems, how to work with the different data systems that you're going to have to interface with, how to work with IT, and access to, getting access to the data that's coming from the vehicle. And so it's a complex problem that can be solved, but you just have to have the right folks in the room. And finally, it's not just working with MCC or Mission Control at JSC. There's a lot of different groups that are involved when it comes to a mission as big as Artemis 2. And so you need to make sure you have all of the connections both within JSC, but also to KSC and Marshall and Lockheed Martin and elsewhere laid out and understood. So with that, thanks.